This lecture is being brought to you in part by the generous gifts of these sponsors.
Thanks for the introduction, Ken. Today I'm going to talk about humanoid avatar robots for co-exploration of hazardous environments. I'd like to recognize a lot of people that worked on this. Unfortunately, I don't have time to go through all the contributors because probably with what you're seeing, maybe nearly 100 people contributed to it all. Here's our team in Miami for DRC. This was collecting our $1 million check in Los Angeles after getting second place in the finals of the DARPA Robotics Challenge. And this is some of the current members. And I'd like to recognize the two main robots I'll be talking about today come from, so one's Valkyrie, that's from NASA Johnson Space Center, and the other one is the Atlas robot from Boston Dynamics. The version that we have, and we still use both of these robots in the lab, have been for about 5 or 6 years. The Boston Dynamics Atlas version that we're using is one of the older versions. You may have seen their most recent version online doing backflips and running and stuff, so their hardware's coming along really nicely. And as far as funding goes, we've had a number of funding sources, TARDAC, Honda Research Institute, DARPA, and then a couple NASA projects. So I'd like to thank those funding sponsors. Okay, so a lot of words in the title. Let me go through them a little bit at a time. So what do we mean by avatar robots? So by avatar robot, I kind of mean something that you can telepresence into so that you can have your presence in a remote location without having to be there through some sort of device. So there are actually some commercial versions of these. There's probably over a dozen companies that have tried to make money on these. You don't see them very often, so I don't know how well they're doing. We have bought this double bot here we use occasionally, but hopefully there'll be markets for these sort of things. But as you see, they have no arms. They're pretty much like a teleconference device on wheels. They do have some advantages over just having a teleconference, but you can't do much with them. And then, of course, we're always competing with sci-fi. I actually started using the word avatar for these robotic systems well before this movie came out, so not copying it. But in the movie Avatar, you have kind of a MRI-like device you sit in, and it can read your brain waves, and therefore you can somehow, through the magic of movies, teleoperate a biological robot and do things like fly around on these lizards. Another amazing movie that I like is Surrogates, Bruce Willis. Here, he lays on his couch all day wearing some sort of brain interface so that he can get his hair back and look a lot younger. And so he's actually, everybody in the world in this movie is a humanoid robot, kind of just everyone's sleeping on their couch, and of course, things go bad from that. So we don't have those technologies yet. The interface devices we have, some of the virtual reality goggles are coming along really nicely. This is a Vive from HTC that I'll show operating a robot with that. And then as far as the sensors go, we've got good cameras. These laser things, LiDAR, is a spinning laser that shoot along in the world and measuring the reflecting time, and from that knowing where points in the world are. Okay, and I'll show what the data from that looks like. I guess right here. So as it's picking up points, this is real time. It starts building representation of the world. It's just a bunch of points, so it has to determine what that means. So what we typically do is look for flat surfaces that are good to walk on, and then also combining that with your cameras, you can get color information, and it's really good for an operator, and people are coming up with really good algorithms for using that data. So here's one of the humanoid avatar pioneers. Senator Rubio came and we gave him a tour, and in the background you can see Atlas there. He was able to, with just a couple minutes of training, walk over a pile of cinder blocks using the system. Here's our professional operator, John Karff, who was our operator in the DARPA Robotics Challenge, using the headset to control Valkyrie here to pick up some water bottles and recycle them. So you might notice he'll move his arm before the robot does because he's not directly one-to-one controlling it. In this one, he's kind of saying, okay, I want the arm to go there, looks good, go. And then the robot will change its body configuration to be able to get to that reach. So it's doing a lot of computation behind the scenes. The only thing that's being tracked on John is where his hands are and where his head's looking. This is Atlas walking over a pile of cinder blocks, and so gave John the challenge of go over a pile of cinder blocks, grab a ball, move the trash can out of the way, and put the ball in the garbage can as quickly as you can. So this also is real time. I say that because a lot of their videos are really slow, so we speed them up, but not this one. You can see in the bottom right, here John's kind of directly operating it where he's saying where each footstep should be. We also have algorithms for saying, okay, I want to walk over there, which he'll be doing after he picks up the ball, and he'll plan a path and some footsteps. There you saw him just kind of swipe in on the bottom right, the camera view. So everything you're seeing back here is just the LiDAR points. So you get a pretty good representation as a human of what you're seeing, but then add on top of that the camera, and it's pretty good. And we're working on better algorithms for better operator interfaces, and but I think there's quite a bit we can do with just these $500 virtual reality systems. So I was able to complete the challenge in about 1:10. Okay, so that's Avatar robots. So why humanoid? I get this question a lot, and it's a good question. And so first, what do I mean by humanoid? So in my mind, we pretty much try to copy humans, and but a lot of people are against that. Like, oh, maybe you can do better than nature, or why copy when the goal is just to get somewhere? But humans have lots of advantages, and so by humanoid, though, I mean you pretty much have 2 legs, 2 arms. You use the arms mostly for manipulation, the legs mostly for mobility. You've got some sort of head with vision, maybe speech and hearing. You need a good sense of gravity because you're going to have to actively balance, and because you're going to have a bipedal mode where sometimes you're on one foot with, so you have to balance. But you might also have a quadrupedal mode. Humans don't use a quadrupedal mode much, but indeed we are quadrupeds. It isn't a question of making a quadruped versus a biped. It's more, in my mind, a question of how often are you quadrupedal versus how often you are bipedal. So why humanoid? Well, the short answer is go where people go and do what people do. And if you think about where people can go and the things people can do when they get there, it's just incredible. I mean, this is just a small sampling of some of the mobility challenges that we face. And if you think of the different types of platforms, and here I just have 4 samples, and think about what it's like for each of them. So you got the humanoid, quadruped, wheeled, and tracked. Think about what it's like for them and what the major limiting factor is for getting over some of these obstacles. It becomes readily apparent why humanoid has its advantages. So if you have like a large gap, you're limited by your leg length. Well, human leg length is about 1 meter, so you can get approximately 1 meter gap without having to jump. Quadruped could do that if its leg was 1 meter long, so you're talking horse size, not just a little. Of course, a dog could jump, but if you're not jumping, then you're going to be very large to get over 1 meter gap. Something with a wheel to get over 1 meter gap is going to have a meter radius wheel, so it's going to be enormous. And same with something with the track. And if you go through these one at a time, you keep seeing that you got great advantages. If you're trying to get over something like a Jersey barrier, well, you need to be a tank if you've got wheels or tracks, or a horse. But human can get over no problem. Human can get over half-meter step, no problem. All of them do well on slopes. Humans can climb ladders really well in the quadrupedal mode, whereas these other guys, you really couldn't do a ladder at all. And yes, dogs can climb ladders. If you have any question about can animal X do Y, the answer is going to be yes. Just YouTube for it, and you'll find. Here's where humans really shine is narrow passages. So if you take a somewhat overweight 47-year-old male, the distance from chest to back is around 12 to 15 inches, maybe a little bit more if you're carrying a backpack. So you can have 2 sheer walls about that far away and you can get through it. Whereas if you want to get through that with these other type of platforms, they have to be really small. So in some situations, these robots would have to be huge to get to the same place a human can. Sometimes they'd have to be really small, therefore they can't get to all the same places. And then if the gaps are only waist height, they only need to be about 8 inches apart. Your foot itself is only about 4 inches wide. So, and when you're standing on your toes, they're only about 4 inches deep, not even about 3.5. So all you need is little pads throughout the environment about 1 meter apart, and you can get from point A to point B as long as you can set down on those. And those little pads that you're walking on can even be pointy rocks, as I'll show later. Balance beam, you'd have to be tiny with these wheeled robots to get over the same balance beam. And yes, dogs walk on balance beams. And rocks, of course, are pretty hard to get over if there's large gaps between them, stepping stones. I mean, the list goes on. Taking corners, you're very narrow, so you can squeeze around corners nicely. And then when you go in your quadrupedal mode, you can get under things nicely. And then you can reach some high places. I can easily reach something 7 feet on a shelf and grab a book or whatever I'm looking for. So if you put it all together, humans are pretty good at each one of these things. And if you look at all the different things humans can do, and they're pretty good. They might not be the optimal solution for any one of them, but we're not trying to optimize for one thing. We're trying to find general purpose things that can get everywhere a human can get to, whereas the other things have trouble in a lot of them. And you think about where humans can get, it's really incredible in the things they can do. I would argue that they're humans and humanoids, including monkeys and apes, are probably the most mobile land-based animal just by the shape of our body. And we're interested in disaster environments. So here's a typical disaster environment. And Jason here is showing how mobile he is. And try to imagine a wheeled or tracked robot getting through this typical disaster environment. And then we like to do various manipulation tasks, so he needed needed his tennis racket. Okay, so another question a lot of people ask me is, okay, so great, what about hybrids? Why not get the advantages of both wheels and legs? And that's great, and there's been a lot of example robots out there that are hybrid. Some of these are pretty amazing. And humans are indeed hybrid. We can fly through the air, if we're crazy enough, we can jump out of a perfectly good airplane and coast with nothing but a suit. Can go hundreds of miles an hour, we can go on water, frozen water, everything. And there's been some humanoid robots. This is just kind of a toy. I don't think it walks, but it's a good concept. During the DARPA Robotics Challenge, we actually had to ride a vehicle. And I think a great Segway is a great platform for a wheeled robot, a humanoid robot to wheel around on. But whenever we use our hybrid appendages, we take them off before we go through our doors. And it's really doors that are the bane of robots and the bane of our existence. There are lots of robots out in the world, but very few of them are good at going through doors, and none of them as good as a human, especially if there's stuff behind the door or a small door, getting up the steps before a door. And so if you want to thwart a robot, you just go behind a door. And and if you can chain it so that it only opens 8 inches, then humans can pass through it freely, but no robot I know of that's any bigger than my fist can get through it. So humanoid form could. So as far as specialized designs, I speculate that that any robot that's as mobile as a human is going to have, just by necessity, some high center of mass like humans do over some small base of support. Because if you want to walk through these narrow gaps, you have to have a tall and skinny body. It's just plain and simple. And because of that, you're going to have some time when you're supported by some leg-like structure. It might not be something you'd call a leg, but it's going to be leg-like, and that's going to require active balance. And that's really what makes humanoids difficult from a control point of view, is this active balance. So if you think about the ways we can balance, I'll talk about just standing first, is you can move your center of pressure on your foot. So as I'm standing here, I'm kind of wiggling my center of pressure where the force is on my foot in order to balance. If I start falling, I can take a step. And if I'm about to fall off the edge here, I can lunge a little bit because I can't take a step. So that's another another strategy. These are the three major strategies people use, and robots fall under the same physics as people, so these are the three strategies you have to use in robots. There's a couple others that have more minor effects that I won't get into. These are kind of the three big ones. And here you can see John getting pushed. And this is a very calibrated experiment with the push being about equal every single time. And you can see the first time he took a lunge, the second time he took a step, and here he stepped and lunged. Okay? And just show this one more time. So you got the lunge only and using the center of pressure on his foot. So by lunging, he didn't have to take a step. Here he takes a step. And for larger pushes or if you're running and want to stop really quickly, you can take a large step and then lunge. So you can use them in combinations. I'll go through a little bit of why these strategies work, okay? And really thinking about a tightrope analogy and balancing a broomstick analogy kind of explains 90% of why these strategies work. And using these real simple models of walking, you can come up with control algorithms for balance. So if you think about balancing a broomstick, so let's go over some of these terms I've been saying here. So center of mass is if you took all of your mass in your body and kind of figured out where the weighted average was in the middle. So with a human, it's about at the belly button. And your system, to a big extent, will behave dynamically as if all that mass is concentrated, as long as you're not throwing your arms around or lunging. And then your center of pressure is if you look at all your forces on your foot, the little pressures, and average those up, there's going to be some point on your foot where if you replace the ground with a point, which is like a needle, and stand on there, everything would behave the same. Okay, and you can feel where your center of pressure is as you push on the ground. And if you think about walking, has to do with this center of mass acting like an inverted pendulum, while the center of pressure moves from the heel to the toe, and then when you take a step, it moves between the 2 feet pretty quickly, and heel to toe again. Okay? And that captures quite a bit of walking. Here, center of mass of broomsticks is about there, and the center of pressure is right about there. And what's really impressive is that he's also balancing himself at the same time, and there's center of mass there and center of pressure there. So the analogy is, what's the analogy? So as you're balancing a pendulum, the question is, where do you move your hand to keep it balanced? And the answer, well, I guess the equivalent questions of where do you move your center of pressure on your foot in order to balance is equivalent to where would you move your hand on your broomstick to balance. Okay? And so the answer is pretty much underneath your center of mass. So if the stick moves, I need to get back under it, right? But the velocity is important too. If the stick's straight up and down, but it's moving that way, and I want to catch it, I'm going to have to get over here to anticipate where it's going to be. So it's some combination of the center of mass and center of mass position and the velocity that's important for where you should catch the stick. And we refer to this location as the instantaneous capture point. And this is something that me and my colleagues came up with over the years on how to think about walking. So throw some equations up here. So the instantaneous capture point is x sub ICP. It's the center of mass location, offset to account for the center of mass velocity. So exactly what I said in words in the last slide. Let's see here. And the proportional term here is the height of the center of mass divided by gravity and the square root of that. So if you look at human parameters, your center of mass height is about 1 meter. Gravity is 9.81 in meters per second squared. So the square root of 1 over 9 or 10 is about 0.3, which means that your instantaneous capture point is going to be, if you take your center of mass velocity and multiply it by about 0.3, and add that, that's going to say how far you have to step or move your hand from where the center of mass is in order to come to a stop. So for example, if I'm walking at 2 meters a second, which is typical human walking speed, and I want to come to a stop in 1 step, that would be 2 times 0.3, 0.6, so I would have to step about 60 centimeters, which is a normal size step to come to a stop. So as you're walking casually, you usually can come to a stop in about 1 step. If you're going a little bit faster, it might take you 2. If you're going really fast, it'll take you 3. There's very few situations you ever find yourself in where it'll take more than 3 steps to come to a stop, if you kind of extrapolate this out and account for how quickly you lose your energy. Now this equation looks at an inverted pendulum model, but it assumes there's no angular momentum, so you don't have your arms flying around or your body lunging, and constant center mass height. Okay? With an inverted pendulum, it'll change a little bit, and as you're walking, it changes a little bit, so it's not a perfect assumption, but it's pretty darn close. And you can control robots with those assumptions pretty well, especially on flat ground, but even with walking over some moderately rough terrain. Once you start doing high steps, you have to start taking into consideration your center mass height change. So this is a robot we developed here called M2V2, with the point showing balance recovery strategies. And so it's using these ideas for how to determine where to take a step. Okay, so now if you think about the dynamics, how the rate of change, what happens to this instantaneous capture point as you're moving, it moves away from your center of pressure at a rate proportional to the distance between the center of pressure and the capture point. So in equation form, x dot means derivative with respect to time, so the velocity of your instantaneous capture point is proportional to, and this is the same proportionality constant you saw before, but flipped upside down. So it'd be approximately 3 instead of 1/3. And then the distance from your instantaneous capture point to your center of pressure. And what's neat about this is that it's a linear equation, which means that your instantaneous capture point will move on a line away from your center of pressure. And again, this equation assumes no angular momentum and constant center mass height. So using this, what you can do is, here's a overhead view looking down where your foot is. You have your center of mass and your center of mass velocity. You put those together with a 0.3 multiplier to find your instantaneous capture point. Now we know our center of pressure has to stay inside of the foot when we're swinging our other leg. If we have it on this corner, then the instantaneous capture point will move this way. If we have it on this corner, the instantaneous capture point will move this way. So that means where we're going to have to put our hand to balance a virtual pendulum, or where we need to step, is somewhere in this region. And we can only step so far. And it's going to take a while before we step, so we can't worry about this little triangle here. It's this wedge that we have to step into, and we call that the capture region. That's the area on the ground where, if you want to come to a stop in a single step, as long as you step inside that, there's a solution for it. If you step outside of that, there's no solution. You can't come to a stop in a single step. You'll have to take a couple more steps. Or if you step way away from it, like way over here, you'll probably fall down because there won't be time to recapture your balance. Okay? Now, what's nice about the instantaneous capture point, another thing of it moving in straight lines, is that we can plan footsteps out ahead. So this shows kind of the current state where you have a foot and your current instantaneous capture point location. We know it's going to move along lines, and we want to take these 3 steps. So we can really quickly just draw lines back to say the path we want the instantaneous capture point to move in order to take these 3 steps. Now, when we take those steps, the center of mass is going to do this pretty complicated, wiggly thing through it, but the instantaneous capture point will move along straight lines. So it makes the planning problem really, really quick, just using these simple geometry. And you can kind of see this. The blue thing is the instantaneous capture point as the robot's walking. The red point is the center of pressure. So you see it stays on the foot, and then during double support, it quickly goes to the next foot. And the black point is the center of mass. And you see that it kind of does a S shape as it's walking. Okay? So we can use these ideas to balance while plan footsteps over rough terrain. This is Atlas walking over some large rocks on 4 different instances. We're pretty much shooting about 50-50 on these when we run it. Sometimes the robot would fall in a gap. Half the time it did, it could pick its foot back up and keep going. And half the time it did, it fell down. The operator is just looking at the LiDAR points and saying manually where to step in this one. This was before we were doing autonomous path planning, but we should be able to do autonomous path planning over these rocks now soon. Okay, so that's if we assume there's no angular momentum, no mass in your body, if everything's concentrated at point mass. but it's not. You've got a lot of mass in your arms, a lot of mass in your legs, so you can't assume you're just an inverted pendulum. But to understand the rest of walking, you can think about somebody walking on a tightrope using one of these poles to help them balance. And what that pole does is it gives them a really large angular momentum, so by spinning it, he can move side to side and balance better. So without rotational inertia, your ground reaction forces have to go from the center of pressure through to the center of mass, okay? And there's your center of pressure, your center of mass. But now if we think about using our angular momentum, the things we can do is we can lunge our body forward. If we're about to go off a hill, we can go like that, or we can windmill our arms. Or we can move our legs around too, but if you're stepping, it's less of an option. We can think of real simple models of having a flywheel on your body that captures that rotational momentum so that if you were to accelerate your flywheel in that direction, what would happen is your ground reaction force would now shift. And the reason why is because you're only interacting the ground at a point, something has to create this torque, and your ground reaction force is kind of doing that. I mean, it's actually your hip that's applying, or whatever, your muscles that are applying forces, but in order to achieve those forces, your ground reaction force has to shift. And so now instead of pushing the pendulum away as it's falling, you now see that it's pushing back on it. And in fact, if we think about virtually translating that force where it now goes through the center of mass like it did before, it's almost as if the center of pressure moved for free. And so now we can move the center of pressure outside of our foot. We call this the centroidal moment point, or centroidal moment pivot. Now, we don't have flywheels that can spin forever, right? I can just move my body a little bit. So we got to pay that back after time, but it's a quick reaction I can do to prevent falling off the cliff. What's nice about all this is instantaneous capture point dynamics stay the same. The only difference is you replace the center of pressure with a centroidal moment pivot. So you still have that the instantaneous capture point moves at a rate proportional to, at the same proportional constant, the distance between the centroidal moment pivot and the instantaneous capture point and centroidal moment pivot. So we can still do all this planning and things, and now the equation only assumes constant center of mass height. Okay, that's the only thing you have to assume for these to be valid equations that you can use for controlling your robot, and which again is a fair assumption on flat ground. So here we'll show Atlas using its internal angular momentum to balance on a line. This is a plywood turned sideways. So, humans, we can do this about as well. Maybe, some people a little bit better, some people not as well. I think with a little bit of tweaking, this is one task that we can do better than humans with robots. And the reason for that is the sensors in the robot are really good. Knowing which way down is super important for balancing. Our vestibular system is pretty good, but compared to IMU's inertial management units and gyroscopes and all that stuff, they're just incredible. And then the other reason is the update rate of what's going on in the robot is fast. Typically you're doing maybe 1,000, 500 to 1,000 updates every second. Whereas a human, you just kind of have more delays in your biological wiring system. So tasks like these, robots can do better. Just about everything else, they're much worse currently, but they could start getting almost as good as humans on a lot of them. As far as the one-step capture region goes, when you add angular momentum, what it does is it kind of grows the region, allows you to step in more places if you're willing to lunge your upper body or throw your arms around. Okay, so the primary active balance strategies, again, you can move your center of pressure in your foot, and as long as your instantaneous capture point is inside your base of support, this is a successful strategy. As soon as it leaves, you have to either lunge your body, which can get it back a little bit, or take a step, which allows you to effectively move your center of pressure a large distance. It's like when you're balancing the broomstick, it's like moving it a large distance, right? Okay, and we've taken a lot of this theory and extended it to a few other areas. One is planning over stepping stones, multi-step balance recovery. So if you have say, stepping stones in a pond and you have to plan a few out after you got pushed or something, you can extend this to figure out how to do that. A lot of people have been working on relaxing the assumption of having a constant center of mass site. The equations become more complicated, but it's kind of the same ideas. And then using multi-contact. As soon as you put your hand on a wall or something, you've got so much more controllability over what's going on. I can now like lean way over here with just really small forces. And theoretically, you can see why when you extend these ideas. And then one thing we're really starting to get interested in is in crawling. If anybody's interested, put this up so people on the video can see. This is one of our papers that cover all of that pretty well. So let me talk a little bit about the framework we use for our controller. And I won't get into the mathematical details of this, just kind of say what each block is doing. So you have a high-level controller that is kind of deciding where the robot wants to step, what motions you want to make, and the output of that is telling the rest of the controller what available contacts it has and what motions it wants as far as like its overall body. And then that goes through a quadratic program solver, which then determines wrenches, the forces and torques on the contacting bodies that are available, and what the joint accelerations should be. And then that goes through inverse dynamics calculator. So the equations of motion of what's going on with the robot so that it figures out torques such that if it applies those torques, it achieves all this before it, okay? That's kind of an overview. And so with that algorithm, we can do things like have the robot have its feet on different surfaces and holding another surface and move its body around. Haven't done this much with the real robot yet, but in simulation it works great. And there's a paper if you're interested in that one. So, on to walking on top of pointy rocks. So if you're down by the bay and you want to get closer, you have to walk on pointy rocks. Can't get there with tracks or wheels. This is a really good demonstration of using your angular momentum, upper body momentum on tightrope-like thing. The Gibbon gets a cheat, though, because it can actually grab the rope. All right, so your main challenge is you can't statically balance in a single support on a pointy rock, okay? When you're on it, you have to take another step or you're going to fall. It's detecting contact conditions is hard with the robot. With a human, you essentially sense the ground. You almost see it with your feet because you've got really good sensors. We don't have really good pressure sensors on the bottom of the feet. We pretty much just know where the overall center of pressure is. You have to use what we call leap of faith maneuvers, where you might be rested on two pointy rocks really nicely, but to get to the next one, you're going to have to trust that you're going to get there, because if you don't make that step, you're going to fall. Because again, you can't stay supported on the one. And because of that, you usually need to use some sort of angular body momentum. One benefit of walking on pointy rocks is that you don't have to worry about slipping so much, right? Imagine if you have a sheer rock that's perfectly flat at an angle. If it's more than 45, you can't step on it. You'll just slide down the hill. But if you're walking on a point, you can angle your foot however you want so that you can push into that point so that you don't have to worry about sliding at all. So that's one thing that makes it easier. And you see that here when people walk, here's like a knife edge. First, your foot will be back so that you can push that way, and then once you get over, you want to push the other way so you flip over the edge. So this shows Atlas walking over cinder blocks that are turned on their side, so it's like a knife edge. The robot takes a little time to figure out what its contact conditions are, and then takes a step. And while taking a step, you see it, if it has to use its upper body angular momentum, windmill a little bit, it will. And if it doesn't, it won't. And it might because nothing's perfect, even though mathematically it knows exactly what it needs to do. It might not achieve that because the hardware is not perfect, so it might be off a little bit and need to windmill. So here you can see it using its angular momentum a little bit more. So there's another paper if you're interested in that. Okay, so moving on to body path and footstep planning. So when you want to avatar one of these robots, you might not necessarily want to control every single detail of what's going on, right? I mean, that would be one mode that would be really cool, and that's kind of the mode in the two movies I showed, Avatar and Surrogates. But if you're doing that, you kind of have to have really good sensation of what's going on for it to work. If you're having to place individual footsteps as you're running over something, then you're not paying attention to everything else. So it'd be nice to have things that help the operator, like autonomous path planning is one that we're working on. So the way we do this is we acquire a point cloud using a LiDAR or the stereo cameras. Then from that point cloud, we look for planar regions. And like in this room, you'd find that the ground is all one planar region, that step, this step, and human environment at the top of each chair, you can't step on those. Human environments, human designed environments, and even natural environments have a lot of really good planar flat regions. And even like a road with some gravel, you could detect that as mostly a flat region. So we find all our planar regions that we can step on. Then we break this up into two parts. First, we plan an overall body path, not worrying about where the footsteps are each going to be. And then we can do that by just seeing connectivity of planar regions. So I would see from here that I've got this plane here, that step there, all that, and that I could get from here to there by approximately taking that path, okay, and while avoiding the obstacles. Once we have that overall body path, then we plan the individual footsteps. Okay, and by breaking it up into two parts, we kind of have to do that because of computation. You could skip part 3 and just say, do a search over the entire space of all the possible footsteps you could take to get over there, but computationally that's more expensive. So we do it into 2 stages. So again, here's the LiDAR point cloud I'd shown before. See what the sensor looks like. And you see it took about a second or two to collect those points. That's still one of the limiting factors for how quickly we can do a lot of things with the robot, is how quickly we can get the data acquired and in. So sometimes the robot will take a few steps, pause a couple seconds to get new LiDAR points because there's new things it can see or it's shifted a little bit, and then take a stop and then keep going. This shows finding planar regions. So from those same points that you just saw, it's detecting all the planar regions and coloring them each different colors. And that works approximately in real time. If we tweak it a little bit, we should be able to get that to be real time. And so here you see kind of for this pile of cinder blocks what the planar regions look like, and then after you tell it to plan a path to the other side, the individual footsteps. And you can either plan those out once or plan as you go. Since you can't see on the other side of the cinder blocks, it can't plan the steps down, so it has to be doing this real time as it's going, collecting the new data points as they become available. And then this is showing some simple path planning. Valkyrie wants to get to the present, but Billy keeps blocking the path. So in real time, it'll replan a path. And this is showing Atlas autonomously going over these cinder blocks. Now, one thing you do have to worry about is knowing where the robot is. As it walks, it kind of is using dead reckoning to know where it is. It's counting for how far each step was, but you're going to be off by a couple centimeters each time. So you have to either collect your data really fast as you're walking, or do what's called localization. As you're walking, look at where the environment is and see that, oh, I think it shifted a little bit. Well, really, I shifted where the robot thinks it is. Therefore, I should shift back where I think I am. And then the data I had previously is still valid. But typically, you're losing about, depending on how well the robot's tweaked, anywhere from a couple millimeters to a couple centimeters per step. So, something this far, you could probably plan once, take those steps and be okay, especially with the cinder blocks being fairly large. Okay, so co-exploration of hazardous environments. What do we mean by that? So that's kind of an application question, and there's a lot of potential applications for humanoid robots, probably hundreds of thousands of them, and they're difficult to build. Very difficult, extremely difficult. And I think a lot of people confuse the difficulty with building them with whether or not they'll be useful. A lot of people would say, oh, well, I use a humanoid robot, they're not useful, they would fall down. It's like, well, that's not useful versus hard. That means they're hard. Let's make them so that they don't fall down, or that they get back up when they do fall down, because humans fall down. But there's a lot of potential applications. For avatars, they really only make sense in a place where it's so dangerous or expensive where you still want a human presence. You want to feel like you're there, but you can't send the person, or it's better to not send the person. So you'd still have a human operator. So as far as economics of it, it doesn't make sense if you're doing, a human plus a humanoid doing the task that just the human does. It only makes sense if it's dangerous. And these are kind of some of the application areas. NASA's interested in robots for Mars. Bomb tech robots are a possibility. Maybe firefighting, possibly soldiers. And every single one of these is possibly. Nobody's really sure if these things will ever be economically viable. I hope they are for some applications, but we'll see. But we won't know until we get over the technical details. Before we'll know whether or not they're useful, they have to achieve some sort of acceptable level of performance. But we can play around with some of these applications. So construction, probably not going to be a good application for humanoids to start, but we can think about things, especially for things like planetary construction. If you're on Mars, it might be, if you got to put together your habitats. And what's neat about this video is we're operating the robot by interacting with it through the beam. So as you push the beam around, the robot will move in the direction you're moving. It's not very fast in this demo, but you should be able to make this real human speed, no problem. So maintenance on Mars, you need to do a lot of things like clean the debris off of solar panels. If you think of all the things that Whatley did in the movie The Martian, those could be possible applications. One was he had to go clean his solar panels every day because dust got on them. What's neat about this demo is the operator simply said, here is the square of the solar panel, go clean it. And the robot planned a path, and as you see, the robot's shifting its body because its arm doesn't have as much flexibility as a human, so it has to shift its body in order to do that path. So that's all done autonomously. For firefighting, we got the Pensacola Fire Department to hook us up to the water spigot, and unfortunately, they didn't let us put out a fire. They claim that it wouldn't really look any better than cones, but I don't know. I'd like to put out a fire. The Navy is interested in possibly having robots put out fires aboard ships. And the difficulty there is you have high sea conditions as simulated by Billy pushing the thing up and down. And you have hatches with things you need to step over, plus you're carrying a hose possibly. So certainly not as fast as it would need to be, but without changing the walking algorithm at all, it's able to balance in conditions like this. And maybe you're cleaning house or doing whatever. In this video, John Carfer, operator, this was after the DARPA Robotics Challenge, and we were like, we've got this humanoid robot, we've got a really good user interface, let's see what else we can do. So he just threw a bunch of challenges out there and played around with it to see what he could do. This is sped up 20 times because a lot of this he's kind of thinking through, okay, I would have to do this and this and this. So definitely not very fast. But what's neat about this is that we now know that these robots are physically capable of doing these tasks. Maybe not fast, but if we can speed them up, work on them, we could do a lot of these. And a lot are really challenging because the operator is not feeling interaction forces. The operator is not feeling the broom. When he's turning on the vacuum, he's only doing it by sight. He can't feel the switch. And hopefully we can get better sensors through time so that the operator can feel the interaction of what's going on. But it's really impressive that John could do this without sensory feedback. And still just the same walking algorithms we use for walking without. So here's our DARPA Robotics Challenge entry. This is sped up a bit because it did take us 50 minutes. I'm not going to subject you to all 50 minutes. But if you speed it up by a factor of 15, you can get through it in a few minutes. The first thing we had to do was drive a car. That was actually pretty straightforward and fun. They yelled at us for going too fast. Then you have to get out of the car. That was actually probably the most challenging part, is getting out of the car. Then you have to go through a door. So what you see in here is in the upper left, that is what the operator is seeing. And you can see, so John here is operating. He's a solo operator, but he's got 3 of us talking over his shoulder. I don't know if that helped at all. But But you can see like here, the robot needs to turn a valve. So John puts a valve target in the world, looking at the light, lining it up with the LiDAR points and what he's seen from the camera. And then once that valve target is there, he can say, okay, now run the valve turn algorithm. And it'll start going through the valve turning algorithm. While it's doing that, John's analyzing what's going on, and if anything goes wrong, he jumps in and changes what it's doing. So he can jump around from a higher level to a lower level as he's doing these tasks. Then he had to grab a drill and turn it on and cut a hole through a piece of drywall. That was pretty challenging, just getting the grip on the drill. You know, these hands are just 3 fingers grippers. Robot hands are really hard. I mean, they're harder than the rest of the robot. And there's, you know, hands that are reliable typically only have a couple degrees of freedom. There are some hands out there that have about a dozen or so degrees of freedom, not as good as human, but getting close, but they're pretty fragile. So for the DARPA Robotics Challenge, we just used a simple hand. So after that, he had to go and grab a plug. It's kind of like a magnetic plug, pull it off and put it back in. It took a little bit of lining up by sight. So the data we're getting from the robot is occasionally delayed. And at this point in the competition, it's either delayed or cut off for like 10 seconds at a time sometimes. So we're operating on old data as we're doing it, but it's pretty reliable, but you have to keep getting a visual once the data comes back. So that task took longer than it probably should. For doing the stepping stones, we on the first day we fell down. That was entirely my fault in deciding where to put it. So on the second day, we kind of played chicken here and just took them 2 at a time, and took more than we needed to, and it's, you know, just manually put them out there. But it worked. And then after that, you had to get up some stairs. So you can kind of, you know, extrapolate this. If we can speed it up by about a factor of 5 or so, which I think we can, that, you know, there might be some potential applications for real world things. Again, though, if the robot falls, which is what everybody was paranoid about, which is why we went as slow as we did, you're done with these robots because they can't get back up. So I think getting back up from a fall is what the robots really need to be able to do before we start trusting them and before we can really start using them in the real world. And of course, there's entertainment. Another awesome movie, Hugh Jackman, Real Steel. In fact, all good stories are about love, redemption, and humanoid robots. Okay, so this word "towards" in the title. That's kind of a weasel word that scientists use to mean, you know, we're making progress, we're not there yet, we got a lot of work to do, and therefore we need a lot of funding to get there. But there are some major challenges. I would argue a good portion of those challenges are in the mechanics. You know, a lot of the stuff we're trying to do with humanoid robots work amazingly well in simulation. You try to get them on, and we can develop like 10 times faster in simulation. Trying to get them working on the real robot is really hard because of the components we're limited to. But there's been a lot of enabling trends, especially with self-driving cars pushing technologies now. I mean, just computers are amazing, communications are amazing. Like what you can process, these point clouds are amazing, perception of computer vision. The virtual reality interfaces are becoming amazing. All of these things are really making progress. And non-contact sensors are really amazing. The contact sensors actually feeling forces and things like that. They're getting better, but much more slowly. So here's my humanoid wish list. I won't go over all of it. I'll just mention that one thing that we're going, you know, a lot of these things are things that we don't work on, and you know, we're just relying on what's commercially available. The things that we do work on are robot structure when we design the robots and joint designs, and but it's very humbling looking at what nature can do. You look at what the range of motion of a shoulder is just amazing. So you have a ball and socket joint, which gives you 3 different motions. But not only that, you've got shrug. You can move your shoulder up and down, forward, backwards. So even if my arm's all the way out there, I can still move it back and forth. So you have what we call 5 degrees of freedom in your shoulder, and it's all operated by this muscle that's laid out in such a way, you know, you got about 24 muscle groups operating your shoulder, and they're laid out in such a way that they're over each other and spread out a lot, so that no matter where your arm is, you have a good lever arm on it that some set of muscle can pull nicely with, okay? So, as I move my arm, one set of muscle no longer kind of does any effect on it, but another set of muscle kicks in. In contrast, when we're using things like, so here's some of the muscles, here's some more, and then, you got your pecs and everything, and if you count them, there's quite a few. But copying that is super hard because we don't have actuators that package as nicely as muscle. When you look at some of the specifications of our actuators, like torque and speed and power and all these, they're comparable to muscle, not quite as good. Like hydraulics are super high power, but they're very inefficient. Electric are not as high power, but they're more efficient. But packaging them is really hard. Whereas with soft muscle tissue, you can just put a whole large volume in a very small spot and be able to do things like pull from different angles. If we're doing something like this with linear say hydraulic pistons, what we'll typically do is have one piston per degree of freedom. So for a ball and socket joint, you would only use 3 pistons. Well, trying to figure out how you would arrange those so that as the ball and socket joint moves, you don't lose your lever arm with one of them is very hard. And I apologize for not having a picture. I hope that made sense. But it brings up the question, can we build something that's as good as a human? And I was talking with my buddy Victor, who's working on a new robot design, and he was asking, okay, so what are we shooting for here? And like, well, human gymnast. He's like, okay. Now, Victor's very optimistic, if you've ever met him. And like, no, Victor, you can't. It's like, well, I will try. And I was like, okay, well, look at degrees of freedom, range of motion, power, weight, volume, all of that. See if you can get it packaged in the form of a human gymnast. And so he's originally from Romania, now a Canadian citizen. And so naturally he said, okay, well, we have to name it Nadia. And so here is the current, the mock-up. So this isn't a real robot. This is all plastic, but it's printed plastic that has all the components for the robot. So what we're doing, and 3D printing is amazing for designing robots, because as you're designing, you can quickly just print something like this out and see if all the parts fit, see if things hit, which is really hard to do in CAD. Wow. So and then a nice thing is we have the mock-up of the actuators, and these are actual actuators that you can buy off the shelf, but this is just a printed plastic version. We have them so you can lock them in place. So we can pose the robot. So we have a lot of fun posing the robot. So these are the actuators from a company called Moog. They're 3D printed also in titanium. They have all the components you need, your piston, your sensors, your electronics. Pretty much half the complexity of what goes into a robot, boom, is now in one of these packages, so we can just buy it and focus on the other half of the complexity, which is the joint design. They're a bit pricey still, but if you look at the torque speed curve, this is a torque speed curve. If you look at the torque versus the speed of a typical human knee, you can achieve better than that with hydraulics if you have the right valve, in about the same weight as the muscle. So power to weight. Now this isn't taking into consideration that you need a backpack pumping your fluid through. Electric motors are a typical off-the-shelf one without doing anything fancy, is about half as strong as a human for the same weight. But people have been pushing the envelope on those where it's starting to push towards. But the reason to use hydraulics is just the power density. So some more poses. You can curl it up nicely. Wow. Yeah, we really want to be able to crawl. We just have a helmet on here since we didn't know what to do with the head yet, and we just threw that on there and it looked really nice, or maybe that's what it'll look like in the end. And then we can pose it like going over some typical environments we'd be interested crawling through. So the answer is no, but we can move towards that goal with the right funding. So a final thought, and I'm stealing this phrase or modifying it from Matt Onler, who used to be at NASA and is now at Houston Mechatronics. We live in the century of the humanoid avatar robot. It's going to happen. Eventually, I don't know if we'll ever get better than human, but certainly we'll probably get 60, 80% as far as what a human can do, especially in mobility. Manipulation is another question. Just what hands can do is incredible. So we'll see. We can make some progress. The real question is what decade, and that'll probably be dictated more about if there's economic benefit towards it, if there's some reason why a big company would start working on these in a big way. But we will see. So a couple links, our website, robots.ihmc.us, on YouTube, DRC IHMC Robotics, and most of our papers are on ResearchGate. Thanks for your attention. So take some questions, but we'll pass the mic around, or throw the mic. We have one right here.
I won't throw it. Just talking.
I noticed that all the robots are flat-footed.
Mm-hmm.
We humans have flex in our feet.
Yep.
Feet, excuse me. But have you tried anything
Yeah,
with flex?
absolutely. So on almost every single robot project I've been involved in, we always bring that question up, what should the foot look like? And the answer is always, well, let's put a flat plate there for right now. And later when we have time, we'll figure out how to really do it, and we never get the time. One of the big challenges is getting the actuation for your toes, because trying to fit some motors in the feet is really hard, especially when you need, you saw how big those actuators were for the hydraulic ones. Motors are big and round, so they just don't package there very well. You could put some in the leg and have cables. There are 2 or 3 robots out there in the world that do actuate the toes, and they can stand on the toes. And once you can do that, it's huge advantages because you don't need, as big of an area to step on, and it's, yeah, exactly. For gymnasts, you definitely want it. And then the other thing our foot can do is not as well as the Gibbon you saw, but we can grip surfaces a little bit. And even like on edges, you can kind of go around them a little bit, especially if your shoes are off. And just the complexity to get that would be really hard in the design. So that's typically why we just skip it. But if we could, we'd definitely put it in there. Now we can do passive solutions where you spring load it and not put a motor there, just a spring. And we played around with that a little bit, but haven't really figured out the best way to do it yet. In the back, red shirt. Catch. Careful.
So. Hello. Oh, gosh. How fun is that? Biology seems to favor stereo cameras. And, like a fish eagle can deal with the refraction in the water and get a fish. I see you're using LiDAR. Yep. There's some question, especially you mentioned autonomous driving. Mm-hmm. What do you feel, is LiDAR essential, or can we do everything that biology can do with stereo cameras?
I think you can do everything you want with stereo. And there have been some people building robots who have said, okay, the LiDARs are so expensive and slow and whatever. Stereo is not going to give you as fine a resolution, like you won't know within millimeters where things are, especially things that are far away, whereas these LiDARs are just phenomenal. They'll tell you where, so it's not as precise. So you need a little bit better algorithms to deal with it, but definitely I think you could do everything in stereo eventually. And cameras are getting so cheap, down $1 a pop for the actual components. And the processing algorithms, especially like deep convolutional neural networks for doing vision recognition and stuff, are getting so amazing that perhaps you could do it without LiDAR. We've stuck with LiDAR so far because that was the best sensor we had for the DARPA Robotics Challenge, and we didn't have the algorithms for processing the stereo, but we want to move to stereo. And then there's also other cameras like structured light and things that will do various tricks to get you good point clouds. But anything that develops a point cloud we can use for our algorithms. Yep. That's right there.
Thank you for an inspirational lecture. One of the new acronyms to describe Pensacola is JAPDIP, J-A-P-D-I-P, just another perfect day in paradise. And to add to that, Dr. Saunders, University of West Florida, mentioned this past week there'll be a PhD program at West Florida with the help of IHMC. So explain the symbiotic relationship between West Florida, IHMC, and Pensacola and the military. with that new
yeah.
happening.
Yeah, we're really excited about this program. So it'll be a collaboration between UWF and IHMC, where we'll have a number of PhD students who will be doing their classwork at UWF and doing their projects for their PhD thesis here, and in a number of areas related to robotics and intelligent systems. So I think it was plans to start in about a year, so it should be great. I don't really have more than that, except we're looking forward to getting the first crop of students, and it'll be the program itself will be a little bit untraditional in that the student will be more responsible for self-directed study, and a lot of their coursework or a good portion of their coursework will be online courses, and then some of them that will be kind of directed by some of the researchers. So we'll kind of be more of a mentor than like a lecturer. So should be pretty cool. Yeah. In the back, we got a couple questions.
I throw like a girl and I catch like a girl. I'm always glad to be a lady. Yes, you've been commenting mostly on humanoid robotics for disaster response. To lighten things up, sometimes before you would send those really expensive robots in to respond that can move fire hoses, fire extinguishers, and all that heavy-duty stuff, carry away humans, is there any consideration that you could comment on, whether it's here or other information you have about robotic advances, about an entity that has no problem with walls, ladders, floors, ceilings, drain pipes, ventilation, and most doors that are commercial and residential? Our favorite arthropods, six-legged, affectionately called the cockroach.
Oh yeah, yeah. Yeah, I mean, definitely there's a lot of morphologies that will allow you to get a lot of places, especially if you're small, so like cockroaches, or if you want to get through pipes like snakes. But suppose let's take the snake for instance. Suppose you have a snake and now you want it to be able to manipulate something, so you attach some arm to it or whatever. Maybe you want 2 arms. Well, now you've got a human, right? So give them a couple legs. Oh, for investigating too, yeah, yeah, and also drones. Drones are so amazing, and it's just amazing what drones have been able to do. And it may simply be the case that the role of the humanoid robot is to open the door for the drone to go in. Yeah, we'll see. If the application is inspection or just exploration without a lot of manipulation, but if you have a task where you got to do a lot of manipulation at a large height, then having something with a small base of support with some arms at a high height with active balance.
Okay,
but
let's thank our speaker for an excellent talk.